Swayam Prabha. Digital India. Educated India.
Welcome to another lecture on control systems, and as with the last few lectures, we shall continue to see a few more applications of Nyquist criteria. To start with, we shall see some examples. We actually saw a couple of examples, if not more, in the previous lecture. So we shall see a few more examples so that we get comfortable with the idea of at least qualitatively sketching this Nyquist plot, and then we shall see how at certain critical points you actually need to be more careful. That is where the numerical values, the exact numerical values begin to matter. We have already seen hints of that in the sense that we want to get very accurate about where the Nyquist plot is actually intersecting the negative part of the real axis in the GC plane, right. So apart from that, there are a few other points where we want to be a little more careful. We shall see that by and by, but for now let us continue to see a few more examples of these not the straightforward ones, so rather a continuation of the kind of examples such as the ones which contain open loop poles on the imaginary axis. So if you notice, the last example we had taken was something like this, if I recall correctly. In fact, it is there in the previous slide, yeah. So it is s plus b. So let me just be consistent with that. So it was s plus b upon s squared, right. So this was our example 2. So now let us take another example. Here, in addition to this system that we had earlier, let us suppose we have an additional non-zero pole as well, where of course a and b are positive real numbers, right. Once again, as before, since we are by now very familiar with root locus, let us at least sketch the root locus. So this is the double pole at the origin, yeah. Now clearly you see that there are two possibilities, right. On the one hand, you could have a configuration such as this, where minus b is here and minus a is here. In this case, you can see that the root locus will be something like this. Let me use a different color. So you see that the root locus will be something like this. But what about the asymptotes? We of course know that the number of asymptotes is going to be 2, but what about the centroid? And that is critical. You see, the location of the centroid is given by summation of the poles minus the summation of the zeros divided by number of poles minus number of zeros, right. Now notice one thing carefully here. Of course the number of poles minus the number of zeros, yeah, that is going to be 2 here, yeah. So we know already that this number is going to be 2, right. But what about the summation of the poles minus those of the zeros? You see, this is just a 0, a pole at 0, so this will contribute nothing. But you see, magnitude wise this pole is greater, right. A is greater than B, that is what it means, right. So therefore this means that the asymptote will be somewhere at minus A minus of minus B upon 2. So this is basically going to be b minus a by 2, but from this figure clearly a, because a and b are positive numbers, clearly a is greater than b. So therefore this is negative, right. So along the vertical line that is perpendicular to the obviously the real axis, but on the negative part of the left of the complex plane. So essentially we can imagine that this asymptote would look something like this. In other words, root locus tells us that no matter what you do to the value of this k here, so let me put the k here, yeah, no matter what you do with the value of this k, if you play around with this value of k, at no value of k will you ever find this crossing over from the left half plane to the right half plane, that is the closed loop poles will always remain on the left half plane. So we wonder if the same conclusion can be drawn from the Nyquist plot. You see, we have already seen that with Bode plots, this insight about where the closed loop poles go and all, it's pretty much lost, right. So that's why we want to have a frequency domain equivalent of what we had in terms of root locus, right. So let's see, how do we go about this? As always, when you have a pole on the origin, you have to introduce a dent like so. So let me use a different color. So you have to use a dent like this on the contour. Yeah, as before, of course, we choose it like this. Yeah, so we choose it like this. Yeah. So now, yeah, so this is what it is, right. Okay, now let us again, as before, we label these points as A1, A2, let's call this B, and let's call this C, right, and we have this kind of a pole 0 configuration, right. Okay, so let's see what this point A1 is tantamount to on the, so by now we should be a little more comfortable with Nyquist than when we started off. So let's see, this is real part of GC and this is imaginary part of GC, okay. So what does this point A1 map to? Let's look at the phase. As I always say that in Nyquist, at least in the qualitative sketch, we never really bother too much with the magnitude, right. It is basically the phase that contains all the important information for us. If you are bothered about the magnitude, well then you better get yourself a computer or a calculator at least, yeah, and then make a table of different values of omega and then plot them accurately, right. So what we have seen thus far is only a qualitative sketch, right. Yeah, so there we are. Now with this sort of a contour, we want to map this point A1 on the GC plane. So where does A1 map to? Let us look at the phase. So you see the phase of this point, again just like in the previous example, it is minus 180 degrees, because these two, this additional pole and 0 apart from this double integrator, yeah, just like in the earlier example, if you notice, this additional 0 did not contribute any phase, yeah. Here also this pole and 0, their cumulative effect is also negligible at this point A1, so it is 180 degrees, right. So if the two poles have 180 degrees, since they come in the denominator, the overall effect is to have a point somewhere here at minus 180 degrees, right. So let us say this is my A1 prime, right. Now as I go from A1 to B, what happens? You see, again as before, these two fellows, they will not contribute any additional angle, they will keep contributing throughout this whole segment from A1 to B. You pick any test point, the angle contributed by these two factors, that is this S squared, is going to be always 180 degrees, yeah, the same minus 180 degrees therefore, right. But what about this? Now see that the 0 is to the right of the pole, yeah. So at any point here, the 0 is contributing a greater positive angle than the pole, yeah. So whatever the 0 is contributing, the pole is taking away a bit of it, but still what remains in this segment is still a positive angle. So it is like the effect of this 0 only, like we had earlier, 0 acting alone. You recall this is somewhat analogous to the use of a PD controller and a lead compensator. So just like a lead compensator gave you a phase lead, not exactly the extreme case like the PD compensator, but still it gave a phase lead. So here also you notice that at any test point in the segment A1 to B, yeah, there is effectively a phase lead. What does this mean? You have minus 180 degree plus some positive angle. So you have the net result is like some minus 172 degrees, minus 160 degrees, something like that. But where are these minus 172, minus 160 degrees? These will be somewhere in the third quadrant, because you are going in the clockwise direction is what is counted as a negative angle, negative phase, right. So you go all the way up to minus 180 degrees, and then you are forced to go a little clockwise depending on the contribution of this pole 0 accumulated together. So basically what it tells you is that you are bound to remain in this third quadrant of the GC plane in going from A1 to B. What happens at the point B? Well, of course, as before at the point B, you see the effect of the 0 is 90 degrees, the effect of the pole is also 90 degrees, but there is one critical difference between the earlier plot and this plot. What is the difference? In the earlier plot, you see the 0 contributed at 90 degrees, right, and the pair of poles at the origin, they still kept contributing that 180 degrees, right. So it is minus 180 contributed by the pair of poles at the origin, in this case, that is in the one that you see before yourself, and the 0 contributed a plus 90 degrees. So the net result was a minus 90 degrees, yeah. So therefore you had the B dashed mapped here, but in our present case here, you see this pole and 0, they cancel each other's effect at the point B, because even the pole contributes a 90 degree, right. So the 3 poles, all 3 of them contribute 90 degrees, so minus 90 into 3, that is minus 270, and the 0 contributes a plus 90, yeah. So it is effectively minus 180 degrees. So it is of course still a 0, but with a minus 180 degrees. So where is the minus 180 degrees 0? It is somewhere here, yeah. If we are not too nitpicking about this, then allow me to draw this here. So this is going to be your B prime, okay, somewhere over here. And I also know, as I argued earlier, that at any test point on this segment A1 to B, the phase contribution of this pole 0 net effect is going to be some positive angle, so some counterclockwise additional rotation. So first you had a clockwise rotation of 180 degrees due to these pair of poles at this point, yeah, and these two, the other two remaining pole and 0, the non-zero pole and 0, yeah, that is A and B. So this is minus B, this is minus A. So this minus A and minus B, yeah, they contributed some additional positive phase to it. So that forced your plot. So I am not again bothered about the exact shape of how this came about, but it could very well be something like this. I really do not care about the exact shape. This is anything, like, you know, the only thing is that as I go from here to here, this is how it goes, right. And now I am faced with the question of what happens from B to C. Well, that will be mapped in the vicinity or the neighborhood of this origin here. So what happens at C? You see at C again, I can see that the point C dashed will be mapped somewhere over here. It is a 0 with an angle of plus 180 degrees, yeah. So what is the net rotation? So final at C prime is 180 degrees, initial at B prime is minus 180 degrees, yeah. So the net rotation is equal to final minus initial, that is 180 minus of minus 180, which is equal to 360 degrees. So if it is a 360 degree rotation, yeah, then it is one counterclockwise rotation in the vicinity of the origin, which will look something like this, right. Now once that has happened, once I have been able to draw this, I really do not have to draw for the segment C dash to A2, yeah, because it is just going to be a mirror image of this, yeah. So I am just going to, okay, even if it does not look like a mirror image, that was my intention, to draw it as a mirror image. Again, my drawing skills have gloriously failed me, yeah. So this is kind of like the mirror image, all right, yeah, that is better, yeah. So this is going to be the direction of rotation like this, and we arrive at A2 dashed, which is the map of the point A2. But now what about this small circle here which will probably be manifested by an infinite rotation here. What about this small dent? Now look at A2, what is the phase at A2? Yeah, this A2 prime, it is 180 degrees, right, because the contribution from this pole 0 pair is negligible. Yeah, so this part is going to be very similar to this. Yeah, and you see that we can actually deduce that once again at A2 prime it is 180 degrees, yeah, and at A1 prime it is minus 180 degrees. Yeah, so the net change is minus 180 minus of 180, which is minus 360 degrees, so that means a full clockwise rotation. Yeah, so full clockwise rotation would mean that you go once around like this throughout, and clearly then you see once again as before we can conclude that this point, no matter what you make the value of k, just like we concluded from the root locus, no matter what the value of k, the root locus entirely remained within the left half plane. Yeah, so here also along similar lines we can now deduce that no matter what you do to this value of k in k, this shape will probably change a bit, but the fact that if you draw a test radius, yeah, if you draw any test radius, it will actually cut this Nyquist plot twice, once in the counterclockwise sense, once in the clockwise sense. So n is always going to be 0. Yeah, and of course because you have excluded these pole pair at the origin, so your p is also going to be 0. So no matter what you do, identically z is always going to be 0, which is essentially the same story that the root locus had earlier told us. Yeah, so we see that Nyquist gives us a beautiful way of deducing the same things, only that we do not need to use the time domain tools, we can just stay within the frequency domain, right. So remember we are evaluating g j omega mostly, right. This contour is yeah, I mean this small contour around this origin is what is accounting for parts that are not on the j omega axis, but for the most part this critical part is basically the part that deals with the j omega axis, right, and therefore it is a frequency domain tool, just like Bode plot was. Yeah, that justifies the name that Nyquist is a frequency domain tool, whereas clearly root locus or Routh-Hurwitz were explicit in the time domain characteristics. Right, so now let us turn this around a bit. So consider again the same example where we have again s plus b upon s squared into s plus a, right, of course with a k. So here now instead of considering the location of the pole and 0, we have flipped the location of the non-zero pole and 0, right, and let us look at the root locus. So how will the root locus look now? Well, of course this part does not change, yeah, but what about the other two? Now notice that this is your minus a and this is minus b. So where is the centroid? Yeah, the centroid, that is the point of intersection of the asymptotes. Centroid is given by, of course, the number of poles minus the number of zeros is 2. Now you have minus a minus of minus b, which is b minus a by 2, but crucially here b is greater than a. Yeah, so here we have b greater than a greater than 0, right. So therefore this is positive. So now, yeah, this centroid is somewhere over here. So your asymptotes are these. So now your root locus will look something like this, and it turns out that for no value of, so let me use a different color. So it turns out that from this root locus you conclude that just by flipping the position of this pole and 0, yeah, or maybe toggling their positions, you arrive at the conclusion that now there is no stabilizing positive k. Any positive value of gain k that you apply to this system, the closed loop pole, actually a pair of closed loop poles, will always be on the right half plane. And again we are left to wonder if the same thing can be drawn, the same conclusion can be drawn using our Nyquist sketch. So let us try and analyze that. So now again we draw that same d, of course by excluding the the pole pair at the origin. Yeah, so this is our D contour, always chosen in the clockwise sense, as mentioned so many times. So we call this A1, this B, this has C, and this has A2, and we want to map this on the GC plane. Yeah, so again, needless to say that this is our GC, so that's controller and plant taken together in the unity feedback configuration. Okay, so of course this is the real part of GC, this is the imaginary part of GC. All right. Now, is there any difference between the map of the point A1 here and in the earlier case, in the preceding case? Well, it turns out there is no difference here, right. So, the point A1, let me draw it here. So, the point A1 maps to A1 prime, which is still here. Yeah. Now, point wise if you look, the point B prime, which is the map of this point B, that is also going to be the same, because see the behavior, the phase contribution of this additional pole and 0, whether they are flipped or not, at the point A1 they are both going to contribute 0, at the point B they are both going to contribute 90. So, their net contribution at the points A1 and B are identical and 0. So, it is only those pole pair at the origin that is contributing a phase of 180 degrees at both the points A1 and B. Okay. So, therefore, we can actually draw the map of this point B in the same place like we drew here, which was this. Yeah. So, let me draw that. So, this is going to be our B prime here. Okay. So, this is our B prime, but now where will the difference show up? You see, now if you take any test point over here, say S1, right, what happens now? You see, now the pole contributes a greater angle than does the 0. And what does a pole contribute? A pole contributes a phase lag, right. So, effectively like there is a lag. So, effectively this is like the effect of one additional pole acting alone. What does that tell us? That tells us that at the point A1 prime I already have a phase of minus 180 degrees, and while travelling from A1 to B, that is while tracing this curve from A1 prime to B prime, yeah, I will have additional phase lag, which is addition of more negativity. So, I already have minus 180 and I have some more negative phase. Where will that take me? If I am already sitting at minus 180, which is a rotation of a full clockwise rotation of 180 degrees, that is a half circle, and then some additional incremental rotation, it will take me from the third to the second quadrant. So, therefore, it means that this part of the curve, unlike in the earlier case where it followed and remained throughout in the third quadrant, here it will actually cross over to the second quadrant and then maybe again within the vicinity of 0 again cross over to the back to the third quadrant, or just remain. Yeah, this I mean this B dashed point is, I mean B dashed and C dashed are like infinitesimally separated, right. It really does not matter that much, but yeah, we of course do make a distinction between the two. So, I come over here, right. So, this is going to be my sketch from A1 to B, which is basically this, alright. So, now remember that this gap, although it looks a big gap, it is basically infinitesimally closed. This B dashed is infinitesimally close to the origin. Yeah, I have just drawn it with that gap exaggerated to sort of make things clearer. Now, what about this B to C? Yeah, the same conclusion once again holds, right. You see at B and C again the phase contribution of this additional pole 0 pair is the same. Yeah, so therefore, there will be a rotation like this. Just like in the previous case, here we had a rotation, a counterclockwise rotation of 360 degrees, here also we have a counterclockwise rotation of 360 degrees, and now the remaining part again like I always say, so this is going to be my C prime. So, from C prime to A2 prime, I do not need to redraw this or recompute this, I am just going to draw the mirror image of this here, yeah, and this is going to be my A2 prime, right. Now coming to this A2 to A1, what is the conclusion now? Let's think of this for a while. At A2, what is my net phase? The net phase is 180 degrees, and at A1 the net phase is, so at A2 the net phase is, the phi is contributed by these two, the others do not contribute, so these two contribute 180 degrees, and at A1 the phi that I have is minus 180 degrees. So I am going from A2 to A1, yeah, that is my direction of traversal. So my initial is A2, final is A1. So final minus initial is minus 360 degrees. So that is again a clockwise rotation like before, as before, yeah. So it is basically no difference essentially. The only difference is that there was a crossover of this, and it turns out that that will make all the difference for our purpose, yeah. So let us draw this and then we will see how that is so. So this is our Nyquist plot. Of course this looks finite, but this is an infinite contour, yeah, like in the previous case this is an infinite contour, yeah. So anything in this vicinity of this origin, this makes for an infinite contour like this. Now you see, as I said, this is drawn in an exaggerated fashion, but this is actually very close to the origin. The point, the critical point -1, 0 is somewhere over here. This is my critical point, right. Now you see you are helpless. Why am I saying you are helpless? Because no matter what you do to this value of k, yeah, you draw any test radius, it is always going to have n is equal to what? See, there are two clockwise encirclements, so that means -2 counterclockwise encirclements, so n is going to be -2, yeah. If n is going to be -2, and again as before my p is 0 known to me because I have not included these two pole pair at the origin, this pole pair at the origin, so therefore p is 0, so therefore z, this implies that z is equal to 2, which is exactly what the root locus also told me in this case, right. So I see that even the qualitative sketch of the Nyquist gives me as much information as the qualitative sketch of the root locus. Now if you are interested at what value of k things cross over, here of course it does not matter, yeah, because at any value of positive k you will always have a pair of closed loop poles on the right half plane, just like in the previous case. No matter what value of positive k you chose, this closed loop system will always be stable and this will always be unstable, yeah, no conditioning on this, right. So k is inconsequential insofar as stability is concerned. There is no way you can stabilize this using handle if you have a handle over k, right. So you see that this Nyquist criteria actually allows us to draw all of these conclusions that we drew using the root locus earlier. So I will conclude this discussion on examples with a final example. So it seems like the earlier two examples we have chosen, they are not that interesting in the sense, they are interesting in the sense that you have this pole pair at the origin, so you have to take the dent around it, but it is not so interesting, as in, you know, there is nothing much you can do. If you are just given access to this knob that controls k, no matter how you rotate this knob, yeah, it is always going to be unstable in one case and it is always going to be stable in another case. So there is no transition really from stability to instability or the other way around. So in order to illustrate that, let me take a final example, and hopefully by having seen these examples, after having seen these examples, you would be fairly confident and comfortable in sketching Nyquist criteria, almost as comfortable as you are with root loci. But I must warn you that all this I am doing at a qualitative level, right. So I am not really computing this. We will shortly get to see why computing those accurate values are critical, and once you do that, you will get exactly the same information that Routh array or root locus gives you. So here is our final example. So our GC is going to be s plus alpha squared by s cubed, okay. So let us take a look at something like this. So again, as we are more comfortable with root locus, having seen too many of them, let us first draw the root locus for this. So we have 3 poles now at the origin, yeah. So 3 of them here and a 0 pair at minus alpha. So this is minus alpha, right. So then how does the root locus of this look like? Yeah, there's going to be just one asymptote, yeah, because the number of poles minus the number of zeros is 1. So of course from this also you know that this is how one of those asymptotes is going to be. So of course at some point here there's going to be a break in, yeah. So one of those poles, one of those 3 poles is going to just terminate here, and among the other 2 they will, okay, here's the crucial bit I missed. So let me be a little careful about this sketch. Yeah, again a qualitative sketch if you would. So here's how it would look, right. So as many branches, how many branches? 3 branches, because there are 3 poles. So 1 branch, 2 branch and 3 branches, 1 branch, 2 branches, 3 branches, right, first, second and third, and then 1 branch terminates at infinity along the 180-degree direction, the other 2 branches terminate at this 0 pair, okay. Now why did I draw this root locus to bend around to the right? Well, it's this angle of departure, recall. So what does the angle of departure around this tell me? So if I apply the angle criteria here, let's just refresh our memory a bit on root locus, it helps, right. So what does the angle of departure tell me? So within a small epsilon neighborhood of this, the angle subtended by the 3 poles is, let's say 3 theta, right. So if theta is the angle of departure, so 3 theta d plus theta d plus theta d, yeah. So this, and of course what about the angles from the pair of zeros? It's 0, yeah, it's just going to be 0, because for a viewer at standing at minus alpha, yeah, this epsilon neighborhood of this triplet of poles at the origin, yeah, is not going to subtend any angle whatsoever. So this is going to be some 2k plus 1 times pi, where k is of course allowed to be positive or negative integers. So therefore we have 3 theta d is equal to minus 2k plus 1 times pi, yeah. So we know that this theta d is going to be basically heading along 3 directions, yeah. So you let this k be 0, so it's basically minus pi by 3. So if minus pi by 3 is this direction, then of course you apply k is equal to 1, so you have 2 plus 1 3, 3 pi by 3, that's minus pi, so that's basically this branch, yeah, and finally you allow k to be equal to 2, so 2 2s are 4 plus 1, that's 5, so minus 5 pi, yeah. So minus 5 pi is minus 900 degrees, so that's minus 300 degrees, so minus 300 degrees is basically 60 degrees, so that's this branch, right. So those are the 3 directions along which departure happens. So the angle of departure condition here tells you that this is going to be a conditionally stable system, because initially when you start increasing the value of k from 0, initially your closed loop poles migrate to the right, yeah, until after a certain point they have to cross over back to the left, yeah. So here is a typical example of a conditionally stable system where actually increasing the gain leads to stability. Remember when I spoke about this motivation behind Nyquist, yeah, people often deal with open loop stable systems, and that's why there is this folklore that positive gain margin and positive phase margin and things like that, that's what tells you about stability from the Bode plot. But then suddenly when you encounter systems like these where it turns out that increasing the gain is good for stability, it's a little difficult to wrap your head around it if you just look at the Bode plot, right. So that's why Nyquist promises to help us out with this, yeah, just like root locus did here. So let us test that out. Does Nyquist really help as promised, or will we be disappointed in this newly developed Nyquist criteria that we've just studied, okay. Right, so let us draw the contour as before. So here it is, this triplet of poles here, and this is this pair of zeros here at minus alpha. So let us draw this D contour here like this, yeah, okay. So this is A1, this is B, this is C, and this is A2. So this is how it's traversed, yeah, this is in the Argand plane. Now let us go to the GC plane and try and understand what's going on here. Okay, so this is the real part of GC, this is the imaginary part of GC, right. So what happens? Again, as before, let us try and figure out what's the story with this point A1. So where does A1 map? So this time I am going to do a bit of mental calculation, maybe not take so much trouble and write everything down. I urge you to pay attention and follow this and do your calculations on your own, that will give you some practice. So look at this point A1, what is the total contribution from this triplet of poles? That is all that is going to matter, right, at this point, because all the other fellows, the phase contribution hardly makes a difference, it does not change, yeah. So if I look at this, it is going to contribute 90, 90, 90, so that is 270, but because these are poles, it will be minus 270. What is minus 270? Minus 270 means that it is going to rotate clockwise from this reference line, that is positive real axis. So clockwise rotation of 270 degrees, that is 3 quadrants. So it is going to go once, this is 90, then this is 180, then it is 270, right. So somewhere over here, okay, right. So somewhere over here it is going to start off with, okay. I do not really know what the exact sketch is going to look like, but then if it starts off over here, what happens at B? You see at B, at this point B, what is the net phase contribution? These fellows still keep contributing that minus 270 degrees, but now this pair of zeros, they will contribute 90 plus 90 or 180 degrees. So this net contribution is minus 90 degrees. So you have to end up, so if this is going to be your A1 prime, the map of A1 under this GC, yeah, then what about this B prime? This B prime apparently is going to be somewhere over here, yeah, it's going to be somewhere over here along this direction, no. So therefore clearly at some point there is going to be a crossover, there is going to be a crossing of this negative real axis, and this should really interest us, yeah, this really interests us, and once we are done with this complete sketch, you will see why it interests us. So before we get into that, just observe, just make an observation, this segment A1 to B, whatever we are drawing, or in the earlier case when you did not have a dent from A to B, your Bode plot only gave you that much information. So far as the frequency domain information is concerned, you only drew for positive values of omega, Gj omega for only positive values of omega, yeah, but Nyquist clearly is doing more, it is plotting way more than that, right. So it is not really surprising that Nyquist tells you more or gives you more information, yeah, so that is just a point I wanted to make, right. So now let us get back to here, this point here. So this is A1 prime and we have come all the way from here. So of course if there is this crossing, then we better evaluate this, yeah, so that is not so hard to evaluate, it turns out. So you just substitute this j omega plus alpha whole squared upon j omega whole cubed, and what is this real axis crossing? It is the point where the imaginary part is 0. So you just take the imaginary part of this is a complex variable equal to 0 and solve for omega, yeah. So this solution, this finite solution for omega is going to tell you where it crosses over. So clearly this might have multiple solutions in general, yeah, there is no guarantee that there is going to be only one solution, so there can be multiple solutions. In fact, there will always be, if there is a omega, there is always a minus omega, that is what this picture tells us, that it is going to be symmetric. Anyway, probably I am getting ahead of myself here. So the moment you encounter something like this, that there is a crossover, remember in the earlier case also you had a crossover, but you already saw that it is going to happen in the vicinity of the origin, right. So we did not really care, one happens in the vicinity of infinity, the other happens in the vicinity of the origin, and in between this infinity and this origin, it is bound to remain in the same quadrant. Yeah, we can argue about that. So we do not really have to even solve for this, but here if you have to get from the second to the third quadrant, at some point you have to just cross over, yeah, possibly an odd number of times, I do not know, right. So that whether it is going to monotonically cross over like this, maybe we can say something qualitatively, let us take a look. So as before, let us take a sample point here, let us call this S1. So what happens here? You see this is going to contribute, if this is theta, then this is going to contribute 2 theta. So this triplet of poles, this triplicate of poles, this is always going to contribute at 270 degrees. But what about this fellow? As you go from A to B or A1 to B, yeah, as you keep moving up, the contribution of these 0 pairs is doubled in the positive direction, right. So that means it is tantamount to a counterclockwise rotation. So basically if you draw phasors from here and here, you see you are rotating in the counterclockwise direction, right. So it is going to, at least the phase is going to monotonically come like this, okay. So maybe this is a reasonable sketch, unless I have better ways of drawing this sketch more accurately, that is if I tabulate them and plot the magnitude and all, this for my purpose kind of suffices. Of course this is one point that should interest me, so I should better evaluate it by solving for this, that is going to be critical. Okay. Now what about from B to C? Again you see here it is going to be this, so I can immediately sketch the point that C prime is going to be somewhere over here, yeah. So if C prime is going to be somewhere over here, then along what direction am I going to go from B prime to C prime? So at B prime the angle is minus 90 degrees at B prime, and at C prime what is the angle, just take a look, it is going to be 270 degrees due to the poles and minus 180 degrees due to the zeros, right. So it is going to be a plus 90 degrees, so a plus 90 degree at C prime. So the net change in the phase is going to be from the final to the initial is going to be a 180 degree. So therefore it is going to be a counterclockwise rotation. So of course I repeatedly keep saying this, that this small dent here is hardly of any consequence, yeah, this really does not matter insofar as our stability deductions are concerned, but if you want to be particular about this, better draw it accurately. Now again I am going to apply the same trick here, I am not going to evaluate for this C to A2, I know that it is going to be the mirror image, so I am just going to draw this like this, yeah, and here is where now I will end up with at A2 prime, right. Now the question is from A2 prime to A1 prime, which is the map of A2 to A1, the small dent that I drew around this origin, in what direction am I going to traverse, yeah. So that is going to be a critical question here, right, insofar as the stability is concerned. So let us see, at A2 prime what is the phase, yeah. So what was the phase at A1 prime? So A1 prime is this map, so at A1 prime it was minus 270 degrees, so here it was, the phi was minus 270 degrees, here the phi is 270 degrees, the phase is 270 degrees. So if I am now desirous of going from A2 to A1, so my destination is A1 final point and my source or my starting point, initial point is A2. So I better subtract the phase at A2 from the phase at A1, yeah, that is my direction of traversal. So A1 is minus 270, so the net phase change is minus 270 minus of 270, yeah. So this is at A1 prime and this is at A2 prime. So that is going to be minus 540 degrees, which means a net rotation of 540 degrees in the clockwise direction in going from A2 prime to A1 prime. So 540 degrees is basically one complete rotation of 360 degrees and another 180 degree rotation, of course all in the clockwise sense. So then what does this mean? This means that, of course this is at infinity, so it might look a little sort of counterintuitive. So, this is one complete rotation and then another complete rotation like this, yeah. Again I take no responsibility for these dents, yeah. Okay, so here we are, and now this is interesting. Why am I saying this is interesting? So consider two scenarios. Now if you keep playing around with this k, yeah, this point, remember, this point will shift to the left if you increase k, and this point will shift to the right if you decrease k, yeah. If you decrease k, it shifts to the right. So what is desirable for me in this case? I wonder. See here again I want, so I have this n is equal to p minus z, yeah, and I know that excuse me, and I know that this p is going to be 0 because I have excluded these triplet of poles at the origin. So this is going to be equal to 0. Now if I want z to be equal to 0, yeah, what should I want n to be? If z has to be 0, then n better be 0 as well, yeah. But notice if I am decreasing gain k, yeah, if I am decreasing gain k, then this point where this imaginary, this real axis crossing happens, it moves to the right. So at some point you will see that this critical point of minus 1 comma 0 is to the left of this point where this real axis crossing happens, and then I am in trouble. Why? Because now if I draw a test radius like this, the number of encirclements n is going to be equal to minus 2, but if n is equal to minus 2, then you see here z will also have to be 2, which is exactly the situation of this segment here, yeah. So here also I have seen that between this segment of this root locus, yeah, this now portion that I am marking now in this color blue, yeah, this segment of this root locus is for low gain, and at low values of gain I see that my closed loop poles are in the right half plane. Here also I see that if I make my gain values very low, yeah, I will eventually end up with a situation where this point minus 1 comma 0 pops to the left of this this crossover, yeah, and therefore I have two encirclements. On the other hand, if I increase k, this point, this whole thing blows up, balloons out, yeah, and therefore I will eventually arrive at a situation where this is going to be my point minus 1 comma 0. And what about a point that is inside this? Now I draw another test radius like this. You see there is one encirclement in the left counterclockwise direction and one encirclement in the clockwise direction, and this is exactly as I desire. So n is equal to 0, leading me to conclude that z is also going to be equal to 0. So this is basically the other segment. So now I have chosen a sufficiently large value of gain k, and that high value of gain k has taken me from the brink of instability to closed loop stability, okay. So this is exactly consistent with our understanding of the stability, the closed loop stability as we saw in terms of root locus. Only thing is you have to be careful about what these angles are, how they are going about, and if you are cautious about how to plot these segments, yeah. And as I have now shown you also this other segment, this small dent that you have taken, yeah, this is going to play a very important role, yeah, because this dent is effectively telling you that there is going to be these two encirclements, yeah, and that n is going to be minus 2 clockwise encirclements. So the number of counterclockwise encirclements is minus 2, and that n is equal to minus 2 tells me that z is going to be 2, which is the undesirable situation. So low values of gain are undesirable, which probably the Bode plot I would have been hard pressed to reduce, but from the Nyquist I can now clearly deduce all of these conclusions, okay. So hopefully with these sort of examples that we have now taken, you will find that you are more or less comfortable and more familiar with Nyquist plot. Of course you will have to practice quite a lot more to familiarize yourselves even further, but at least I hope that you have got the hang of it, at least how to deal with these Nyquist plots, given that you have to solve for them, okay, or given that you have a transfer function, you have to deduce about the stability at least qualitatively, at least how you can go about your business. At least you would be able to say whether it is always stable irrespective of the value of k, or always unstable irrespective of the value of k, or it is conditionally stable. Now if you want to evaluate the value of k at which this crossing over happens and all, then you have to be very careful and compute these crossover frequencies, yeah, and at that particular frequency what is the value of this gain k, and all these sort of things, right. So the critical value of k will be when this crossover, yeah, this crossover happens at exactly -1, 0. So that is going to be the critical value of this gain k here, right. So now having seen all of this at least qualitatively, we are in a good position to understand the notions of phase margin and gain margin, but in order so as to not confuse you and make any blanket statements, whenever I am going to talk about phase margin and gain margin, I am going to implicitly assume, yeah, because if I do not assume that I will be in trouble. So I am going to implicitly assume that the system is at least open loop stable, that is all the open loop poles are in the LHP, in other words P is always going to be 0, right, because if that, once I make that assumption that P is always going to be equal to 0, then I just need that N to be equal to 0 in order for Z to be 0, yeah. So then at the back of my mind I can always have this preconceived notion that I do not want encirclements are bad, I do not want any clockwise encirclements, right. I want to exclude the critical point, that -1, 0, I want to exclude it, and it better be outside of my Nyquist plot, yeah. So that is what it is, right. Or in other words, if you have a situation like this for instance, then I want as many clockwise encirclements as the number of counterclockwise encirclements. So in that case the net number of encirclements is still 0. So I want, if the encirclement is inevitable, yeah, then at least let it encircle in such a way that the net number of encirclements is still 0, yeah. So this is true only if P is equal to 0, that is your open loop system is itself stable to start with, right. So based on this understanding we shall now venture into comparing between these notions of gain margin and phase margin as we understand based on Bode plot and say Nyquist plot, okay. So what we will take is a typical transfer function, the one that we are very familiar with. Let us take GC to be equal to some k upon S plus A into S plus B into S plus C, yeah. So now of course I already know the root locus of this, so we will probably, I will just draw the root locus and we will continue with the Nyquist and the Bode part of it, yeah, and then we will hopefully be in a position to compare. So this is, let us say, the root locus, this is the Bode plot, and this is the Nyquist plot, okay. So of course the root locus is going to be something like this, you have 3 poles here like this, right. So you will have a segment of the root locus here and another segment that goes like this, yeah, and somewhere here it will tend to go over to the right half plane. So it all depends on what choice of k you have made. So my first situation is where I have made a k choice such that my closed loop poles are here, okay. My second situation is where I have made a choice of k which is exactly the critical value, okay. So this is going to be my critical value of gain k, that means, okay, so that means that I have my closed loop poles on the imaginary axis, okay. And last case we will consider when, of course this whole thing will change We will first consider these first two cases and we will see how they manifest themselves in terms of the Bode plot and the Nyquist plot. Okay, maybe we can actually take the unstable case and we will consider the other as a special case. Let's draw the root locus for these three cases. So this is after you have increased the gain to such a value, yeah, that it's already gone berserk, it's already gone unstable, yeah. So then in that case your closed loop pole is here, yeah. So this is what root locus is fairly transparent, it's pretty straightforward, you can exactly see where the closed loop poles are from the root locus, exact locations are obtainable from the root locus. So one is when your values of gain are lower, yeah, so it's common knowledge, right, that when your open loop system is stable to start with, initially you start at the open loop poles, so for lower values of gain you will remain in the left half plane, but for higher values of gain k there is a risk that you might go to the right half plane, not always, but in this case as you can see that there are three unsatisfied poles, unsatiated, so of course there will be three asymptotes, so two of them will migrate to the right half plane, so that's inevitable. So then we have this in one case for lower values of gain k, so this is for low k, this is for critical k, and this is for high k, okay. So we understand root locus fairly well, we have sketched this. In the next lecture we shall see how the Bode and the Nyquist, which are the frequency domain tools, how the Bode plot and the Nyquist plot for this particular type of system, they happen to look like, and we will try to interpret the phase margin and gain margin from those plots, okay. Already from the Bode plot we know how to do it, from the Nyquist plot now we will do the same thing, so all in good time.